Hello everyone, welcome back. In today's lecture, we're going to be looking at indeterminate forms. So often when we've been evaluating limits, sometimes we are not able to just plug in the x value of interest because we have something go wrong in the denominator, for example. We have like a 0 or something like that. So this lecture begins to cover all those different odd scenarios where you have something like 0 over 0 or other weird things that happen that aren't exactly real numbers. So we're going to touch on a few of those forms today, and I'm going to show you some algebraic techniques for handling situations where you have indeterminate forms that arise, okay? So I'm going to jump right in with an example. And often with this material, just seeing all the different types of examples is a great start to understanding how to handle this entire lecture. So I'm just going to go through kind of the typical examples you see in this section. So first we have the limit as x goes to -4 of 1/4 plus 1 over x over 4 plus x. So we have this kind of complex fraction happening here. And what happens if you plug in -4? Well, not only do you get a 0 in the numerator, but you get a 0 in the denominator as well. So I'm going to write 0 over 0 in parentheses. That's not a real number. This is one of our indeterminate forms. We're going to visit many different types of indeterminate forms today, and then even in later lectures, I'm going to introduce additional indeterminate forms. But 0 over 0 is one of the ones we're going to look at today. So what happens in this situation where you try to evaluate this and you get 0 over 0? One way to approach something like this is you could try to use algebra to manipulate the original expression. So let's try to do that. So the limit as x goes to -4 of this expression, one thing I could do is I could multiply the top and the bottom by the least common denominator of all the fractions. So if I were to pretend for a moment that 4 was over 1 and x was over 1, if you look at all 4 of these denominators, you would require a 4 and an x, and that would be your least common denominator. So over here, I'll write that the least common denominator is 4x, and I'm going to multiply this entire fraction by 4x over 1 over 4x over 1. Okay, so I've multiplied by a form of 1 here, and you can think of this as distributing 4x to every single term in the numerator and the denominator. So let's look what happens. Here, you get 4x over 4x. So that's just going to, or sorry, 4x over 4. That's going to cancel to x. Now we'll go to this second spot. Here I'll do 4x times 1 over x. The x's cancel, and I just get plus 4. This is divided by, now I'm in the denominator here, 4x times 4 is going to give me 16x. And then 4x times x will give me x squared. So it looks much different. We don't have many fractions anymore. The reason for picking the least common denominator is I cancel all the denominators. So now I just have one fraction to deal with. If you look at this -4 and try plugging it in now, you get 0 over, and you get 0 again. So we're still not quite there. However, we do have another trick up our sleeve, and that's factoring. So this is equal to the limit as x equals -4 of x plus 4. Factor out what's in common. They both have a 4 and an x. So bring out a 4 and an x. And you're left with 4 plus x. This is good because now if you see the numerator and the denominator, they have a factor of x plus 4. It's in a different order, but I mean, it's the same factor. So we can get rid of that, and we get 1 over 4x. And we've kind of gotten rid of the problem now, because now, before you couldn't plug that in because you get 0 over 0, but now you can plug in -4, and you're going to get 1 over 16. So you can evaluate limits like this sometimes. It just takes some algebra. So if you see a complex fraction problem like that, that's usually the way to handle it. So this is just kind of the most typical example. Let's look at another example. And this time it involves a bunch of radicals. So we're going to do the limit. I actually forgot to write limit. I tend to do that very often when I'm doing problems like this. The proper way to do it is you're supposed to write limit in every single step until you actually evaluate the limit. So once I plug it in, then I was able to drop the limit. You're supposed to keep it the whole time. I tend to forget, but I'm gonna try my best to remember. This is going to be the limit as x goes to 0 of the square root of 3 plus x minus the square root of 3 all over x. And let me separate. Just kind of go like that. All right, so naively, you'd always want to just try plugging this in. You never know when it's going to work. Sometimes it does. So if you try plugging it in and you get a real number, generally that's the limit. If I plug in 0, I get root 3 minus root 3 is 0 over 0. So again, I'm putting that in parentheses because that's not actually a real number. This is a type of the indeterminate form. It's the one we just looked at. What could you do in a situation like this? Well, if you see radicals like this, and it's like a binomial, so two terms, you can always try using the conjugate. So what I'm going to do is this time I'm going to multiply the top and the bottom by the conjugate of this. So it's root x plus 3. Instead of minus, I'm going to do plus root 3. And then you have to do the same thing on the bottom here because you need to multiply by a form of 1. So this will be the trick this time. So once you've seen enough examples, you'd be like, OK, this is the one I use least common denominator for. This is the one I use conjugate for. And there aren't too many other examples, but I'm just trying to give you the strategy for each problem. Here we are going to multiply. So we chose this because it's going to cancel all the radicals in the numerator. So this is equal to the limit as x goes to 0. If you multiply a radical by itself, the radical is just gone. So I have 3 plus x. Notice you have a difference of squares. So this one times this one is just the opposite of this, or sorry, this one times this one. The two outer ones are the opposite of the two inner ones. So you don't have to multiply those out because the outer and the inner cancel. So the left, what's left is you multiply the two last ones. This times this will be minus 3 over. I encourage you to not multiply out the denominator, or don't multiply out the one that was not a difference of squares. So multiply out the difference of squares, this one. Do not multiply out the other one. So this is going to be x times radical 3 plus x plus root 3. So I've just left it like this times this. I didn't multiply it in. If we continue, I have the limit as x goes to 0. 3 minus 3 will just leave me with x on top over x radical 3 plus x plus radical 3. This is the whole reason why I didn't multiply this out, because you can see this factor and this cancel. So now I'm left with the limit as x goes to 0. Remove these x's here. I get 1 over radical 3 plus x plus radical 3. At this stage now, you can plug in 0. So before I couldn't do it because I'd get 0 over 0. But now if you plug in 0, you're going to get 1 over root 3 plus root 3. And this is just 1 over 2 root 3. So notice I kept the limit in every single step. I'm proud of myself for remembering. I kept it until this very last moment. And then when I actually plugged it in, and then I dropped the limit. I don't need it anymore. But until then, you need it in every other step. So this is the limit of the original problem. Let's do trig stuff, because we did all that practice with trig, and there's going to be trig functions in your limit problems. So I'm going to give you one right now. This is the limit as x goes to 0 from the right. So this is a one-sided limit of x times cotangent of x. So what happens with this one? Again, try plugging it in the beginning. You get 0 times, and then for cotangent, what happens at 0? Well, we'd have to think about the graph of cotangent. So if we drew that here, what I'm going to need to do is I'm going to need to figure out where are the asymptotes of cotangent. So cotangent of x. This is kind of one of those quotient rules that you should have memorized. So this is not sine over cosine, but cosine over sine. It's basically like you've just flipped tangent. So then, where is sine undefined? Well, not where sine is undefined. I'm sorry, I misspoke. Where is this going to be undefined? It's when sine is 0. So where is sine of x equal to 0? I'm asking that because once you make the denominator 0, you've made this one undefined. So this is 0 at 0, and also at pi. So we know our asymptotes are going to look something like that. OK, and then it turns out that instead of going this way, like a typical tangent graph would go, cotangent goes this way. And at pi over 2 right here, right in the middle of 0 and pi, at pi over 2, if you plug that in, cosine is 1. Oh, sorry, cosine is 0. So cotangent of pi over 2. Cosine is 0. And sine is 1. So that's why I have this point right here. So it looks like the tangent graph. It's just kind of pushed over a bit and also flipped. OK, so I did that just so I can show you what happens to cotangent. So when cotangent is going to 0 on the right, let's look at the graph. We did this in the other limit videos. So here's 0. If you're on the right side of 0, you're doing this. Where are you going? You're going up forever. So this is infinity. So we have 0 times infinity. This is an indeterminate form. And it's actually the second one we've done so far. So the first one we've looked at is 0 over 0. This one is also indeterminate. There's no real answer for 0 times infinity. It's almost like you don't know which one's going to win out. So you think 0 times anything is 0, but infinity is not a real number. So this is indeterminate. We don't know what that is. OK, so all that means is we need to do something to the original problem so that we can turn this into a form where we can actually evaluate the limit. So let's think about what we could do. One thing we know is that cotangent is cosine over sine. So let's change it into that. So we'll have x and then cosine over sine. OK, so this is nice. However, if I plug in 0, I'm still going to get 0 over 0 now. I just have a different indeterminate form. But I'll get 0 over 0. So that doesn't help us at all. So again, I'm putting it in parentheses because that's if I were to pretend to plug it in, I'd get this number, but it's not a real number. Let's play with this a little bit. So this is equal to, the limit as x goes to 0 on the right. This is cosine over sine over x. So what I've done is I've moved this x to the denominator of this denominator. If you don't believe me that these are equal, all you need to do is do keep, change, flip, cosine times x over sine. That's how you deal with dividing by fractions, right? And you'll see that it equals the original. OK. Now, if you think all the way back to one of the first videos we ever did on limits, we did this limit right here, sine of x over x. I drew a picture of what it looked like. What was the limit of this? As x approaches 0, this was 1. You can go back to that video and find that. And if you plug in 0 for cosine, you get 1. So I actually guess I don't need the limit symbol anymore because I went ahead and evaluated it. So this is equal to 1. So that's what this limit is. It's kind of weird that I wrote it as 1 over 1. It's just 1. I was just doing each piece separately. OK, so if you have trig functions, it's a good idea to know the picture because that could be helpful. And also, it's good to know all these other identities so you can transform it into sines and cosines. All right, the last example I'll do before I take a brief pause here and catch my breath. I tend to not do that very often. It's going to be the limit as x goes to 0 on the right of 1 over x minus 1 over x squared plus x. So again, I always encourage you to just try, see what happens. If you take a very small number to the right of 0, and you do 1 divided by that number, what's going to happen is that this piece is going to go to infinity. 1 divided by an extremely small number, and it's positive, gets arbitrarily large. Minus. Here, the same kind of situation happens. You're going to have a 1 over x squared. That's a very small positive number, and this is also a very small positive number. So if you add two very small positive numbers, it is a very small positive number. So we have this thing that kind of looks like some kind of funny face or emoji or something. Infinity minus infinity is the third indeterminate form I'm visiting in this video. It's not the case that infinity minus infinity is 0 because they're the same thing. They're not. Neither of them are real numbers. We don't really know if this is exactly this. They're both infinity. They're not real numbers. So this is an indeterminate form. We've got to do something to these fractions to fix this. The way you handle this is you get common denominators. So what you're going to do is kind of look at this and see what is the least common denominator. Here I'll factor out this x just so we can look at it more. So I have x times x plus 1 if you factor that. So it looks like the least common denominator is x times x plus 1. That's everything I need to cover both of these fractions. And I've got everything I need here, so we don't have to worry about this fraction. This fraction is just missing the x plus 1. So I'm going to do limit as x goes to 0 on the right. Multiply this by x plus 1 over x plus 1. And leave the second fraction alone. OK? This is equal to the limit as x goes to 0 on the right. Now that they have the same denominator, you can put these together. X plus 1 minus 1, if I simplify the numerator, it's going to be x over their shared denominator, which is x plus 1. If you notice at this stage, I still can't plug in 0 because I'd get 0 over 0. But we have the cancellation, which is very nice. So we get the limit as x goes to 0 on the right of 1 over x plus 1. And wouldn't you know it, you can actually plug this in now. So if you plug in 0, you're going to get 1. So that's what this right-handed limit is equal to. OK, so I'm just going to take a moment to erase this, take a breath, and then we'll do some more indeterminate forms stuff. So see you in just a second. So now we're going to go back to the concept of limits at infinity that we visited back in lecture 6. So often when you look at a limit at infinity, you create indeterminate forms. So we'll look at that, and we're also going to look at how you use the limit at infinity to find horizontal asymptotes for the graph. So we're going to do all of that in the next few sections of this. So let's start with the definition. So we'll denote by the limit as x goes to infinity of f of x equal to L. That's going to be the limit of f of x as we increase x without bound. So what that means is you can just imagining going to the right forever, I guess. And if I wanted to modify this and just make it negative infinity, then I would be going to the left on the graph forever. So when we consider the limit as x goes to infinity of f of x and the limit as x goes to negative infinity of f of x, we are looking for the horizontal asymptotes of f of x, of the original graph. So this is how you properly find the horizontal asymptotes. Let's look at an example. So my example is going to be the limit as x goes to infinity of 1 over x. I started with this one because this is a picture we should already be familiar with. I'm going to draw it right here. This is not the tree trunk. That's x squared. What is this one? It's the one that I didn't really have a picture description for. There's a piece here in the first quadrant, and there's a piece here in the third quadrant. So just looking at this, you should be able to tell me what the horizontal asymptote is, right? It's right here. You are never going to be able to evaluate this and get 0. You can't plug in any real number here and get the value 0, but you could get any other value. In fact, the graph shows you that. So the limit as x goes to infinity, so x goes without bound on the right, if you follow the graph forever, technically, and I walked all the way off screen last time I did that, it's 0, because it's approaching 0. It never quite gets there, but you expect it to eventually go to 0. So this is equal to 0. Notice if you went the other way, and so the limit as x goes to negative infinity of 1 over x, you would just be walking this way forever, but it's the exact same limit. So this is also 0. Doesn't matter that it's negative or positive infinity. Take a look at the graph. This also goes to 0. So there's one horizontal asymptote, and it's at y equals 0. In fact, I'm going to tell you right now that at most, a graph has 2 horizontal asymptotes. That's the most it can have for a real graph in the real plane. So I guess I'll just tell you that right now. It's not in my notes. I just thought of it right now. Let's look at a different example. So let's look at limit as x goes to infinity of x squared minus 4x cubed over x cubed plus 2. So here, if we were to plug in a very large number, the largest power here that we'd be dealing with would be x cubed. And there's a negative sign in front of it. So in the long run, you'd have infinity to the third power here, and it'd be subtraction. So I'd have negative infinity on top. Here, my largest power is the third power. So this term would kind of take over the denominator, and I'd have positive infinity in the denominator. This is an indeterminate form. That word says indeterminate, I promise. So before we had infinity over infinity, I believe. If we didn't, then I have it now. So that's an indeterminate form. So this doesn't equal -1 or anything like that. We have to do something about this. So what I'm going to do to handle this algebraically is I'm going to divide everything by the largest power of x I see. So that's going to be 3 if you look at every single term. So divide every single term by x to the power of 3. So I'll do it in the numerator, and I'll also do that in the denominator. So I'll do 1 over x to the 3 over 1 over x to the 3. I can do that because x is going to be a very large number. It certainly won't be 0, right? So this is valid. X will be much larger than 0. Now I'll go ahead and distribute this in. This is going to be the limit as x goes to infinity. If you go ahead and take care of this, it's 1 over x minus, and here I have 4. So x cubed divided by x cubed, they cancel. Here I'm going to have 1, and then this will be plus 2 over x cubed. So let's take a look at this. So just like over here, where we had a constant, 1 over x, if you take x to be extremely large, this goes to 0. So basically, the general rule over here is if you see any term that has a greater power of x on the bottom, it overtakes the numerator, and that term becomes 0. So 1 over x, if x goes to 0, we just did that over there. This is 0. 4 is just 4. Remember, the limit of as x goes to something of a constant is just the constant. So we actually have -4 because there's a negative sign here. This is a 1. Here I have a constant, 2, over a power of x. So this is 2 over a huge number. That's going to go to 0. So this limit is just -4. And you may recall this as one of the horizontal asymptote rules that you learn in pre-calculus. If the power of the numerator and the denominator are equal, you just take the leading coefficients. So it's -4 over 1. So that is the same thing. This is just the way using algebra to show that that's true. So what I'm going to do here is I'm going to remind you of all 3 of those rules. So moving forward, If the problem is standard enough, you don't really need to go through all this process. You'll have the rules in your back pocket, and then you can save yourself some time. So let's go ahead and go over those rules again. So for a rational function, and we'll say it's f of x equals a polynomial on top, p of x, divided by a polynomial on the bottom, q of x. I'm writing, but you're not seeing that. So if 1, the degree of p of the upper polynomial in the numerator equals the degree of q, then the limit as x goes to infinity of f of x is the ratio of the leading coefficients. So I wrote this example first because this is the one we just saw, right? Here they were both 3. Power of the numerator, the degree of the numerator was 3, degree of the denominator was 3. So you just took the leading coefficients. You just did -4 over 1. For my second rule, if the degree of p is greater than the degree of q, then the limit as x goes to infinity of f of x equals, and let's think about that. So if the degree is larger, so let's say it was x to the 4th over x squared. So this one would grow much faster than this. What happens if you take a very large number and divide it by a constant? Remember, this is equal to x squared over 1. This will go to infinity. And I suppose if I put a negative sign in front of it, it could also go to negative infinity. So this will go to plus or minus infinity. How that translates to horizontal asymptotes is that there wouldn't be a horizontal asymptote. So you'd say there's no horizontal asymptote. That's what that means. Finally, the third one is if I flip it. So that if the degree of q is larger than the degree of p, then the limit as x goes to infinity of f of x, we did that example over here, the very first one. The degree of the numerator here is 0. The degree of the denominator is 1. So here, the degree of the denominator is bigger. What happened? It's 0. So that means this limit is 0. So that's all 3 of those horizontal asymptote rules that you remember, summarized in terms of the limits. After this, I guess what I'm going to do is do a few more examples of finding horizontal asymptotes, as well as another example of just using these limits. So I'll see you very soon. OK, so let's do a few last examples where we find horizontal asymptotes as well as another limit of a rational function. So I'm going to start with this one down here. And I left my rules up here so you can grab which one you need. So I have the limit as x goes to negative infinity of 5x over 17 x squared minus 4. So if you compare the degrees of the numerator and denominator, which one of these rules would apply? I guess I was calling the numerator p of x and the denominator q of x. So which one of these would I consider? It would be this rule right here. The degree of the denominator is larger than the degree of the numerator. This one's 2, this one's 1. So when you take the limit as x goes to infinity, and it actually doesn't matter if it's positive or minus infinity, you're going to get 0. So this limit is going to equal 0. And that's how quick we can do that using our rules. So it is good to be able to do it algebraically. Here I would divide everything by the largest power of x, which would be 1 over x squared. However, this is one of our rules. And I can also say that this means that we have a horizontal asymptote for this graph right here. If this was the graph of our function, if this is the equation for our function, then its graph would have a horizontal asymptote at y equals 0. So that's what that means graphically. OK, let's take a look at finding the horizontal asymptotes of this. So to do that, if you recall, we need to find two separate limits. So the first limit you need to do is the limit as x goes to infinity of f of x. I guess you don't need to do this one first, even though I said that. You can pick either of these to start with, but you need to do them both eventually. So you're going to both look for the limit as x goes to infinity of f of x and when x goes to negative infinity f of x. So this is the limit as x goes to infinity of 2x, or 2e to the x over 5e to the x minus 3. Well, this isn't really a rational function because we don't have polynomials, but the same kind of idea applies to this. These both grow at the same rate. I know as x goes to infinity, what happens to e to the x? Well, if you look at e to the x, it does something like this. As you go off to infinity forever, e to the x goes to infinity as well. So as you increase this without bound, this also grows without bound. Knowing the graphs, when you get stumped on a limit problem, knowing the graph of the function you're working with is so helpful because graphically it's very easy to trace where limits are going. So I really encourage you to just know a lot of these standard functions and their graphs. So what I know is that e to the x is going to infinity. Let's play around with this a little bit. Let's do some algebra. I'm going to divide every single term by e to the x. So if you divide this by e to the x, you get 2. If I divide this term by e to the x, I get 5. And if I divide 3 by e to the x, I get 3 over e to the x. I was allowed to do that because I'm not dividing by 0. We know x is going to be a very large number, so e to the x is going to be a very large number. It will not be 0. It can't be 0 because there's this horizontal asymptote at 0. So now, if I wanted to evaluate this limit, let me do it above because I'm noticing that I might run out of room for this one. Let me go right over here. I have 2 and 5 are constants. That's not going to get affected by this limit. So I have 2 over 5, 3 over a very large number. A constant over something going to infinity. This goes to 0, and I have 5. This tells us that one of the horizontal asymptotes is going to be y equals 2/5. At most, a graph can have 2 horizontal asymptotes. So potentially, I have another one that I'm looking for. And where is it going to come from? It'll be this calculation right here. So we'll take the limit as x goes to negative infinity of f of x. That's the limit as x goes to negative infinity of 2e to the x over 5e to the x minus 3. So what happens in this case? Well, I can go ahead and take this negative and apply the negative sign where I have x's. So I'm going to change this now to be the limit as x goes to infinity, and then I'm going to go ahead and plug in my negative. It's like plugging in -1. So I'm going to have 2e to the negative x over 5e to the negative x minus 3. What do you do when you have a negative power? Well, you flip to the other side of the fraction. So I'm going to, I need some room, so I'm going to scoot this graph. Okay, now I'm probably just going to erase it. We're just going to erase the graph. So let's do like that. I say that, but then I'm going to quickly draw it down here because I think I want it. So this will be the e to the x graph. Flipping this to its denominator, this is going to be 2 over e to the x. So to take care of this negative power, you flip it to the denominator. So this is 2 over e to the x. This is 5 over e to the x minus 3. Now we know as x goes to infinity, e to the x goes to infinity. So I have 2 over a very huge number, 0. And actually just stop there, because here I would get 0 minus 3. And 0 over minus 3 is just 0. So there is a second horizontal asymptote. It's going to be at y equals 0. OK, so this time we have 2 horizontal asymptotes for the graph. Let's look what happens in this final example, and I'm hoping that this is enough space to do it. So we're going to find the horizontal asymptotes of this graph right here. So this means I'm going to take the limit as x goes to infinity of f of x. And I'm also going to take the limit as x goes to negative infinity of f of x. Starting with the top one, I have the limit as x goes to infinity of the square root of x squared plus 1 over 3x minus 5. Now, how am I going to take care of this? It's very similar to how I was evaluating the limit of those rational functions. So I'm going to find the largest power of x and focus in on that. And this radical is going to present a problem, but I'm just going to change the form of the power of x I'm going to use. So if you take the square root of x squared, you get x. Also, the power of the degree of the denominator is also like x. So I'm going to choose 1 over x as what I'm going to multiply by. So this is going to look like the limit as x goes to infinity of 1 over the square root of x squared times 2x squared, radical 2x squared plus 1 over 1 over the square root of x squared times 3x minus 5. So all I've done from this step to this step is I picked this particular expression because I'm going to be able to multiply the radical into the radical here. So I've matched the powers of x. Now, one thing I need to warn you about is that something's working here in the background. So we have to go back to our friend, the absolute value function from lecture 1. So remember the absolute value function of x. And I need to give myself some more room so I can actually write that for you. So let me do it right here. So the absolute value of x says that this is equal to x when x is at least 0 and negative x when x is negative. It turns out that the square root of x squared is actually equal to the absolute value of x. You can take values for x positive and negative and plug them in to each side, and you'll see that that's true for all x. So this is actually equal to the absolute value of x, which is equal to this. So I have to keep note of this rule as I'm working through the rest of the problem. So just keep that in mind. So when I look at this, I'll go to the next line here. Now that it's radical x squared, I can distribute this in, and I'm going to get the limit as x goes to infinity of radical 2x squared over x squared plus 1 over x squared divided by, I need to look at what 1 over radical x squared is, and I'm going to look at that using this rule. So here x is going to infinity. So does that mean x is going to be larger than 0 or smaller than 0? You'd be in the first case, right? Because x is going to be larger than 0. It would be very large. So this square root of x squared is going to equal x. So this will be 1 over x, 3x minus 5. Continuing with the algebra, I would have the limit as x goes to infinity. The x squareds cancel. I get 2 plus 1 over x squared over, distribute this, I get 3 minus 5 over x. And now this just brings us back to our rule we saw earlier, where if you have a power of x in the denominator that is larger than the numerator, then these terms go to 0 as x goes to infinity. So here I'm left with the square root of 2 over 3. So this is one of our horizontal asymptotes. Y equals the square root of 2 over 3. Let's look at what happens when I consider the limit as x goes to negative infinity of f of x. So this is going to be the limit as x goes to negative infinity of the square root of 2x squared plus 1 over 3x minus 5. I'm going to do the same algebraic step I did before because it worked. So I'm going to multiply this by 1 over the square root of x squared, just like I did earlier, to the numerator and denominator. OK? So from here, what I need to do is I need to figure out what this is equal to when I have a negative number that I'm plugging in. In fact, I'm plugging in a very negative number. So the only thing that changes is that this piece will be affected by this definition. So here, when x is negative, like we're dealing with this limit, you get negative x for this value. So that means this is equal to the limit as x goes to negative infinity. The denominator is 1 over negative x. I realized I just made an error. I'm so sorry about that. This is not my original function. It's this right here, 3x minus 5. So all I did with the original here is I multiplied by 1 over root x squared on the top and the bottom. So these should stay the same. Sorry about that. This right here is 1 over negative x because of the definition, times 3x minus 5. This remains unchanged right here, what I did in the numerator. So this is still the square root of 2 plus 1 over x squared. I've just jumped to this step right here because it's identical. Now what happens, I have this negative x distributes in here. I'm going to get the limit as x goes to negative infinity, square root of 2 plus 1 over x squared. This is going to be negative 3, and then plus 5 over x. And now I can evaluate that limit. As x goes to negative infinity, this again goes to 0, and this again goes to 0. And now the only difference is I have root 2 over negative 3. So my other horizontal asymptote is root 2 over negative 3. So again, this is another example where you evaluate both the positive infinite limit and the negative one, and you get two different values for the limit. So this graph, if you were to go on Desmos or something like that and graph it, you'd see there'd be two horizontal asymptotes, and this would be where they are, here and here. All right, I think that's enough for indeterminate forms and horizontal asymptotes. I will see you in class. As always, please ask me questions. Check out your lecture quiz. And yeah, I'll see you next time for lecture 9. Bye.